The Center for Connected Multimodal Mobility, or C2M2, an international award-winning USDOT Tier 1 UTC, is at the forefront of advancing science and technology to solve transportation problems of today and tomorrow. C2M2 is utilizing the power of quantum computing, including quantum AI, to make the transportation cyber-physical system safer and more efficient and secure.
What are the differences between classical and quantum computers? Classical computers are usually deterministic, while programs in quantum computers are intrinsically probabilistic. Classical computers containing wires and logic gates use bits as the smallest unit of information, which can be either 0 or 1. A combination of several bits is used to represent more complex information, and logic gates implement various calculations using Boolean algebra in classical computers. Quantum computers use qubits as the smallest unit of information, which can represent data in 0, 1, or any proportion of combination of 0 and 1. Quantum computers include quantum circuits that combine wires and various quantum gates and mathematically reach solutions using linear algebra. With fully connected qubits, the quantum computer provides an exponential increase in processing power by a factor of 2 to the power of n compared to n in classical computing. Can you imagine the computation power for 1 million qubits? Current research in quantum artificial intelligence mostly relies on designing quantum artificial intelligence for classical data. Decoherence, hardware efficiencies, and mechanical errors in quantum computers can make it harder for the existing quantum artificial intelligence to learn the underlying data patterns affecting their performance. These gave rise to hybrid quantum classical algorithms. At C2M2, our goal is to develop hybrid AI algorithms that can improve safety, security, performance, and efficiency of different multimodal transportation applications. Now let's discuss our first case study of the resilient hybrid quantum classical AI model for autonomous vehicle traffic sign classification under adversarial attacks. Our experiments showed that hybrid quantum classical models are more resilient under adversarial attacks on AI-based autonomous vehicle sign recognition systems. The hybrid quantum classical models provide a stable classifier that can correctly classify images for autonomous vehicles during adversarial attacks. We divided the training stage of the hybrid quantum classical algorithm into 3 parts: a feature extraction unit with ResNet-18, where we reduce the image dimension to 4 input values for the quantum layer. Next, a quantum processing unit takes the input from the previous layer to qubits, introduces variational quantum layers to train the quantum circuits, and uses a measurement layer to convert data from quantum state to classical state. Finally, a post-measurement quantum layer is introduced, which is used to test the final classification of signs. During an adversarial attack, perturbations are added to the input image to fool the model. In our experiments with the quantum processing unit and post-measurement layer, we test how the introduction of the quantum layer in deep learning model can improve classification accuracy and resiliency of the model. We created and evaluated 140 quantum circuits and selected the one providing the highest sign classification accuracy for autonomous vehicles under adversarial attacks. Our second case study is conducted for a cloud-based cyber physical systems environment where a vehicle canvas is connected to the cloud using a CAN logger attached to the OBD2 port of a vehicle. Our experiment is conducted on the CAN bus dataset containing different fields such as CAN ID, data, and timestamp as shown here. In the amplitude shift attack, the amplitude of a feature of the in-vehicle network data is shifted up or down by a random constant value within the time interval. This random value can be both positive and negative, which is added to the original values of a feature. In the hybrid quantum classical neural network, first we pre-process the in-vehicle CAN bus dataset and construct a CAN image dataset. Then, we perform feature extraction using a classical convolution neural network, or CNN, convert the output from the classical CNN into quantum data, and use the quantum data into a quantum neural network to detect an in-vehicle cyber attack. We have performed hyperparameter optimization to obtain the best cyber attack detection accuracy for each type of neural network. As you can see in the table, the required number of trainable parameters is significantly reduced when we use the hybrid quantum classical neural network model, while the cyber attack detection accuracy is the highest, which is about 94%, if we use the hybrid quantum classical model.
With the creation of the Quantum AI Laboratory headquartered at Benedict College, C2M2 has laid the foundation to develop solutions to multimodal, complex transportation issues.
In the C2M2 Quantum AI Lab, our students are working on quantum computing research supervised by several of our PIs. Some example projects include applications of quantum AI in adversarial attack detection and mitigation in autonomous vehicles, pedestrian safety message generation, automated truck platooning, and traffic incident detection.
The Center for Connected Multimodal Mobility is poised to advance quantum computing applications in multimodal transportation systems while contributing to our nation's technical advancements in AI and quantum computing.